Welcome to another deep dive. Today we're going to be talking all about snowflakes.
Oh, cool.
So get ready to learn all sorts of cool things about their formation, their unique shapes, and even how scientists try to categorize them.
It is amazing how much science is packed into something so delicate and seemingly simple.
Yeah. I mean, we all know that snow is frozen water, but I'm betting there's a lot more to it than that. Like, how do snowflakes actually form? It can't just be water freezing in the air, right?
Well, it's a bit more intricate than that. You see, snowflakes, they need a starting point, a nucleus, which is basically a tiny particle that water molecules can kind of latch onto and freeze around. And these nuclei are much rarer than the ones that raindrops form around. Like, imagine searching for a tiny specific grain of sand on an entire beach.
Whoa.
That's kind of what it's like for, a water droplet looking to become a snowflake.
So not just any particle can become a snowflake nucleus.
Exactly. And once that water droplet finds its perfect nucleus and it freezes, it sets off this chain reaction. The surrounding air is usually supersaturated, meaning it's holding more water vapor than it should at that temperature. So the ice crystal, it starts to grow, pulling in water molecules from the air, and actually it's taking them away from nearby water droplets.
Interesting.
This process is called the Wigener-Bergeron-Findeisen process.
Oh.
And it's why snow can be such an efficient form of precipitation. So a small amount of snow can translate to a significant amount of water.
That's so cool. So these tiny ice crystals are competing for resources, and the snowflakes are winning. It explains why a seemingly light snowfall can still pile up so quickly. Okay,
Ooh.
so we've got these ice crystals growing in the air, but what about those iconic six-sided snowflake shapes we all picture?
Right. Well, that six-sided symmetry is actually directly tied to the hexagonal crystalline structure of ice itself. So it's like a blueprint that dictates how the water molecules arrange themselves as the crystal grows. However, within that hexagonal framework, a whole range of shapes can form depending on the temperature and humidity the snowflake encounters, on its journey down to Earth.
So every snowflake has that six-sided structure at its core, but then its specific shape is determined by the atmospheric conditions it encounters.
Precisely. It's like a sculptor starting with a block of ice and then chiseling away at it based on the specific temperature and humidity levels. Now, we often think of snowflakes as those perfectly symmetrical single crystals, but what we usually see falling from the sky are actually snowflake aggregates. These are clusters of multiple ice crystals that collide and stick together in the atmosphere.
Wait, so those big fluffy snowflakes that I see falling are actually made up of many smaller snowflakes that have kind of joined forces.
Exactly. And these aggregates can get surprisingly large. The Guinness World Record for the largest aggregate snowflake was 15 inches wide.
15 inches?
Yeah, that's bigger than a dinner plate.
That's huge. I always thought those perfectly symmetrical snowflakes were the ones that were landing on my coat. Okay, so we've got these snowflake aggregates forming. But here's a question that's always bugged me. If ice is clear, why does snow look white?
Ah, that's a great question. So it all comes down to how light interacts with the snowflakes. Those intricate crystal facets, they act like tiny mirrors reflecting sunlight in all directions. And because sunlight is made up of all the colors of the rainbow, when it gets scattered by millions of snowflakes, our eyes perceive it as white.
So it's like a massive shimmering light show, but happening on a microscopic level. That's awesome. Speaking of shimmering, we've all heard that saying, no two snowflakes are alike. Is there actually any truth to that?
Well, that's a bit of a tricky one. It's incredibly unlikely to find two naturally occurring snowflakes that are exactly identical, especially on a molecular level. However, scientists have actually created nearly identical snowflakes in controlled lab environments by carefully replicating the temperature and humidity conditions.
Really? So they've managed to control the chaos of snowflakes formation.
Exactly. They essentially they created a tiny artificial cloud where they could precisely control the microenvironment. But in nature, with countless water molecules and ever-changing atmospheric conditions, the odds of two snowflakes following the exact same growth path are practically zero.
Okay, so no two snowflakes are alike might not be entirely scientifically accurate, but it still captures the incredible diversity and complexity of snowflake formation, right?
Absolutely. Each snowflake is truly a unique creation shaped by its own individual journey through the atmosphere.
This is all so fascinating. I'm realizing that there's so much more to snowflakes than meets the eye. Let's talk about the different shapes they can take. I'm particularly intrigued by those beautiful branching patterns like Dendrites. What determines whether a snowflake will form into a dendrite, a plate, or a column?
To really understand that, we have to delve into the fascinating work of Ukichiro Nakaya, a Japanese physicist who dedicated his life to studying snowflakes. He meticulously grew snowflakes in his lab, carefully controlling the temperature and humidity to see how these factors influence their shapes.
I've heard of him. He's the one who created that incredible snowflake morphology diagram, right?
Yes.
The one that shows how different snowflake shapes form under, like, different conditions.
Exactly. That's right. His research was groundbreaking. He discovered that temperature plays a crucial role in dictating the basic form of a snowflake. For example, at temperatures between 0 and minus 3.5 degrees Celsius, thin, plate-like snowflakes are more likely to form. But as the temperature drops to between minus 3.5 and minus 10 degrees, the shapes shift toward hollow columns, prisms, or even needle-like structures.
Wow. So it's like snowflakes have their own, like, temperature-dependent personalities. But what about humidity? How does that factor into the equation?
Humidity, or more specifically the level of moisture saturation in the air, it influences how intricate and complex those basic shapes become. If the air is below saturation, the crystals tend to be denser and more solid. But if the air is supersaturated, meaning it's holding more moisture than it like theoretically should, the snowflakes become more elaborate and ornate, like those delicate dendrites you mentioned.
So it's like humidity acts as a sculptor, refining the snowflake shape within those, like, boundaries set by temperature.
Exactly, and that's just the beginning of snowflake classification. While Nakaya's diagram laid the groundwork, later research by Magono and Lee delved even deeper into the nuances of snowflake morphology.
Okay, this is where it gets really interesting. I've heard of Magono and Lee's classification system. They identified, like, 80 distinct snowflake shapes. Tell me more about this system and what makes it so comprehensive.
So Magono and Lee expanded on Nakaya's work, taking into account even more subtle variations in shape. They categorized snowflakes into 8 main groups, with each group containing an array of subtypes. For example, they have a category called capped columns. Picture a columnar snowflake with delicate plate-like crystals sprouting from its ends.
That sounds beautiful. What other, like, fascinating categories did they come up with?
Well, they also identified bullet rosettes, which look like clusters of tiny bullet-shaped crystals radiating from a central point. Then there are grapple-like snowflakes, which are basically snowflakes that have been heavily rimed with tiny water droplets, giving them a more granular appearance. What's truly remarkable about their classification system is that even within a seemingly simple category like needle, there's a vast diversity. You can have simple needles or combinations of needles intertwined and radiating in various patterns.
It sounds like an endless kaleidoscope of icy possibilities. We've got Nakaya's diagram showing the basic shapes dictated by temperature and humidity, and then Magono and Lee's system adds, like, a whole other layer of complexity and detail. But there's one more piece to this puzzle, right? You mentioned a classification system for snow after it falls.
That's right. There's the International Classification for Seasonal Snow on the Ground, which focuses on how those individual snowflake crystals transform and interact with each other once they've landed, forming the snowpack we're all familiar with. But before we dive into that, let's take a closer look at some of those more peculiar snowflake shapes, like those rare triangular snowflakes.
Triangular snowflakes. I thought the six-sided symmetry was like a fundamental law of snowflake physics.
Well, it's definitely the most common pattern driven by that hexagonal structure of ice crystals. However, nature loves to throw in a curveball now and then. At a specific temperature, around minus 2 degrees Celsius, the molecular arrangement shifts slightly, favoring a threefold symmetry instead of the usual 6.
So even within the rigid world of crystal structures, there's room for a little bit of rebellion.
Yeah.
I love that. Do these triangular snowflakes have any intricate patterns like their six-sided cousins?
They can. While they might not have the same kind of branching dendrites you see in classic snowflakes, they can still exhibit beautiful symmetrical designs within their triangular framework.
It's like nature showing off, saying, like, look, I can create beauty and complexity even when I break my own rules. It makes you wonder what other surprises are hidden within the world of snowflakes.
Exactly. And speaking of surprises, we were talking earlier about those nearly identical snowflakes created in the lab. That research is truly a testament to the power of scientific inquiry.
It really is. Can you walk us through how they managed to pull off such a feat? What kind of setup did they use to create those snowflake twins?
So researchers at Caltech, led by Kenneth Librecht, built a specialized chamber where they could meticulously control the temperature, humidity, and airflow around growing snowflakes. They basically created a tiny artificial cloud where they could manipulate the microenvironment with incredible precision.
So they basically built a snowflake spa where everything is perfectly tailored for those delicate crystals to grow in a controlled way. That's amazing. But why go through all that trouble to create, like, nearly identical snowflakes? What's the scientific value in that?
Well, it all comes down to understanding the fundamental processes of crystal growth. By creating a controlled environment, scientists can isolate the specific variables that influence snowflake formation. They can tweak the temperature by a fraction of a degree or adjust the humidity ever so slightly, and then observe how those subtle changes impact the snowflake's shape.
So it's like they're running controlled experiments to crack the code of snowflake morphology,
Exact.
teasing apart like the intricate dance between temperature, humidity, and crystal structure.
Precisely.
This is all so fascinating. But I have to admit, part of me still clings to that romantic notion of each snowflake being unique, a tiny, one-of-a-kind masterpiece.
And you know what? That feeling is perfectly valid. While the scientific reality is a bit more nuanced, it doesn't diminish the wonder and beauty of snowflakes. Each one still forms through an intricate journey, tumbling through the atmosphere, encountering ever-changing conditions that leave their mark on its delicate structure.
So even if two snowflakes might look nearly identical under a microscope, their journeys to get there were likely very different, shaped by countless tiny, unpredictable variables.
Precisely. It's like comparing two seemingly identical human fingerprints. Sure, they might share certain patterns and characteristics, but their formation was influenced by a lifetime of unique experiences.
That's a beautiful analogy. It makes me appreciate snowflakes even more, knowing that they're not just, static, symmetrical objects, but like dynamic, ever-evolving entities shaped by their individual journeys through the atmosphere. This has been an incredible journey into the world of snowflakes so far.
I agree. We've covered a lot of ground already, and there's still so much more to explore. But for now, we'll take a short break and come back with even more mind-blowing insights into the world of snowflakes. Don't go anywhere.
Welcome back to the Deep Dive. Before the break, we were marveling at the intricate journeys of snowflakes and how each one is truly unique. Now let's shift our focus to a fascinating aspect of snowflake science, how tiny impurities can have a big impact on their shape and structure.
Think of it as like snowflake doping?
Snowflake doping. Okay, you've definitely piqued my curiosity. What exactly does that entail?
So it involves the introduction of tiny impurities into the snowflake's environment as it grows. These impurities can be things like dust particles, pollen, or even minute droplets of various chemicals that are present in the atmosphere.
Gotcha.
And even in minuscule amounts, these impurities can influence how the water molecules arrange themselves within the ice crystal, ultimately shaping the snowflake.
So something as seemingly insignificant as like a speck of dust can influence the delicate dance of molecules and alter how a snowflake grows.
Precisely. Some impurities might encourage certain crystal faces to grow faster than others, leading to more elongated or branched structures. Conversely, other impurities might inhibit growth altogether, resulting in smaller or more compact snowflakes. So it's like each impurity has its own architectural style, subtly influencing the snowflake's blueprint and guiding its growth in unexpected directions.
That's incredible. Nature never ceases to amaze me with its complexity and interconnectedness. Do you have any real-world examples of snowflake doping?
Certainly. One fascinating example is the influence of dust particles on snowflake formation. Studies have shown that snowflakes that grow in environments with higher concentrations of dust tend to have more complex and branched structures. It's as if those dust particles act as additional scaffolding, providing more surfaces for the ice crystals to build upon.
That makes sense. It's like giving those tiny molecular builders more materials to work with, allowing them to create even more elaborate designs. Are there any other intriguing examples?
There are. On the other hand, certain chemical pollutants can actually hinder snowflake growth, resulting in smaller and less intricate snowflakes. And this is particularly noticeable in regions with elevated air pollution levels.
So snowflake shapes could potentially serve as indicators of air quality.
Yeah.
That's fascinating, but also a little disheartening to consider.
It is a bit of a double-edged sword. It highlights the interconnectedness of our environment and how even minute changes in air composition can have cascading effects on something as delicate as a snowflake. However, it also underscores the importance of understanding and mitigating pollution to preserve the beauty and complexity of the natural world.
It's a powerful reminder that our actions have far-reaching consequences, impacting even the tiniest facets of our planet. Now, earlier we discussed this fascinating concept of snowflakes acting as frozen records of past weather events. What are some of the possibilities and challenges in deciphering these icy archives?
Yeah, so that's a captivating area of ongoing research. Imagine analyzing ancient layers of ice and snow, deciphering the snowflake patterns to reconstruct historical weather patterns, potentially going back millennia.
Wow. That's truly mind-blowing. What kind of information could we potentially glean from these frozen records?
Well, we could potentially track changes in temperature and humidity over time, giving us a more comprehensive understanding of past climate fluctuations. We might even identify periods of extreme weather events like intense snowstorms or prolonged droughts by examining the size and shape of snowflakes preserved in ancient ice cores.
It's as if snowflakes are tiny icy witnesses to Earth's climate history, holding secrets that could unlock a deeper understanding of our planet's past. What are some of the challenges that researchers face in extracting this information?
One of the primary challenges is ensuring the preservation of those delicate snowflake structures over such vast periods. The pressure of overlying snow and ice can compress and deform the snowflakes, potentially obscuring the subtle details that hold those valuable climate clues. Another challenge lies in developing precise and reliable techniques for extracting and analyzing those delicate snowflakes from ancient ice cores without, damaging them.
Yeah. It sounds like a delicate and intricate process, but the potential rewards are immense. If you can successfully unlock those secrets hidden within snowflakes, it could revolutionize our understanding of Earth's climate history.
Absolutely. It's a testament to the power of scientific curiosity and the endless wonders that await us when we delve deeper into the seemingly ordinary.
This deep dive into the world of snowflakes has been absolutely mind-blowing. I'm looking at those fluffy white flakes falling outside my window with a whole new level of appreciation and wonder.
It's amazing how little knowledge can transform our perspective, isn't it?
Absolutely. But before we wrap up our journey into the realm of snowflakes, there's one more fascinating question I'd love to explore with you. We've talked about how snowflakes form from a single nucleus, and we've delved into the intricate shapes they can take. But what about those truly gigantic snowflakes, the ones that break records? How do those behemoths come into being?
That's an excellent question, and it brings us back to the concept of snowflake aggregates. Those record-breaking snowflakes are not single crystals, but rather intricate formations of numerous individual snowflakes that have collided and coalesced in the atmosphere.
So it's a matter of teamwork, with countless individual snowflakes joining forces to create something truly spectacular.
Exactly. The formation of those massive aggregates depends on a delicate balance of atmospheric conditions. The air needs to be sufficiently cold to support snowflake growth, but also turbulent enough to facilitate those collisions and mergers between individual snowflakes.
It's like a delicate dance between temperature, wind, and chance encounters. And when those conditions are just right, the result is a breathtaking masterpiece of icy architecture.
Precisely. It's a testament to the incredible power of nature to create beauty and complexity from seemingly simple ingredients.
This deep dive has been an incredible journey filled with mind-blowing insights and a newfound appreciation for the hidden wonders of snowflakes. I'm starting to think that snowflakes are like tiny, icy microcosms of the universe, reflecting the intricate beauty and endless complexity of the natural world.
I couldn't agree more. It's all about looking beyond the surface and embracing the endless possibilities for discovery that exist all around us.
But before we get too philosophical, there's one more fascinating aspect of snowflake science that I'd love to explore with you. We've talked about the influence of temperature and humidity on snowflake shapes, but what about the role of pressure? Could the varying pressure conditions at different altitudes also play a role in shaping these delicate crystals?
That's That's a brilliant question, and it's one that scientists are still actively exploring. The relationship between pressure and snowflake morphology is complex and not fully understood. While temperature and humidity are undoubtedly the primary drivers of snowflake shape, it's certainly plausible that pressure could play a subtle yet significant role.
Yeah, I'm imagining those tiny snowflakes tumbling through the atmosphere, encountering shifting pressure gradients as they descend. It makes you wonder how those subtle pressure changes might influence uh, influence the delicate dance of molecules and contribute to the unique tapestry of snowflake shapes.
It's a fascinating thought, and it highlights how much we still have to learn about these seemingly simple yet incredibly intricate wonders of nature.
This deep dive has been a whirlwind of knowledge and wonder. I feel like my entire perspective on snowflakes has shifted from seeing them as mere frozen water droplets to recognizing them as dynamic, intricate expressions of the forces that shape our world.
And that's the beauty of scientific exploration, isn't it? It allows us to peel back the layers of the familiar and discover hidden depths of complexity and wonder in the most unexpected places.
This has been an incredible journey. But before we wrap up our exploration of the world of snowflakes, there's one final question that's been swirling in my mind. We've talked about the fascinating possibility of using snowflakes as a window into past weather events, but what about the future? Could our understanding of snowflake science potentially play a role in predicting or even mitigating the impacts of climate change?
That's a profound question, and it speaks to the potential for scientific knowledge to guide us towards a more sustainable future. While our understanding of snowflake science is still evolving, there are tantalizing hints that it could hold valuable insights for addressing climate change. For instance, by studying how snowflakes respond to varying atmospheric conditions, we might gain a deeper understanding of how precipitation patterns are likely to shift in a warming world.
So it's like holding a tiny crystal ball that reflects not only the past, but also the potential pathways of our planet's future.
Exactly. By unraveling the secrets encoded within snowflakes, we might gain valuable knowledge for adapting to and mitigating the challenges of a changing climate.
This has been a truly awe-inspiring deep dive into the world of snowflakes. Thank you so much for sharing your expertise and passion with us.
It's been my pleasure. And remember, listeners, the next time you see snowflakes falling, take a moment to appreciate their intricate beauty and the profound scientific stories they hold. Who knows what secrets they might reveal about our planet's past, present, and future.
Beautifully said. Now, before we say goodbye, let's leave our listeners with a thought-provoking question to ponder. If we can create nearly identical snowflakes in a controlled lab environment, does that mean we could potentially engineer snowflakes with specific properties or shapes in the future? What implications might that hold for fields like material science or climate engineering? It's something to contemplate as we continue to unravel the mysteries of these fascinating icy wonders.
Indeed. It's a question that sparks the imagination and invites us to consider the boundless possibilities that lie at the intersection of science and nature.
That's a perfect note to end on. Thanks for joining us on The Deep Dive. Welcome back to The Deep Dive. We've been talking all about these fascinating snowflakes, how they form, their unique shapes, and even like snowflake doping. But now I want to talk about like the record-breaking snowflakes, the ones that make headlines for their size. How do those like giants even come to be?
Well, those behemoths are actually a result of teamwork. You have many, many individual snowflakes kind of joining forces to create something truly spectacular.
Oh, wow.
We call these snowflake aggregates, and their formation really depends on a very delicate balance of atmospheric conditions.
Gotcha. So it's not like one supersized snowflake, but rather a bunch of smaller snowflakes like clinging together. It's so fascinating how these tiny crystals can like work together to create something so impressive. What kind of conditions do you need for these like massive aggregates to form?
Well, first, you need the air to be cold enough to support snowflake growth. That's kind of a given. But you also need enough turbulence in the atmosphere to facilitate those collisions and mergers between individual snowflakes.
So it's like a delicate dance between temperature, wind, and like chance encounters.
Exactly.
And if those conditions are just right, then you get like a breathtaking masterpiece of icy architecture.
Precisely. It's another great example of how nature can create beauty and complexity from seemingly simple ingredients.
This entire deep dive has been such an incredible reminder that there's so much more to the world around us than, like, meets the eye.
Ugh.
I'm looking at snowflakes in a whole new light now.
That's the beauty of scientific exploration. It allows us to peel back the layers of the familiar and discover hidden depths of complexity and wonder in the most unexpected places.
Absolutely. Speaking of hidden depths, we talked earlier about the possibility of, like, using snowflakes as a window into past weather events. But now I'm wondering, could our understanding of snowflake science potentially play a role in, like, predicting or even, like, mitigating the impacts of climate change?
That's a very profound question, and it speaks to the potential for scientific knowledge to guide us towards a more sustainable future. While our understanding of snowflake science is still evolving, there are some tantalizing hints that it could hold very valuable insights for addressing climate change.
Like, what kind of insights? I mean, it's hard to imagine how something as delicate as a snowflake could help us tackle such a massive challenge.
Well, think about it this way. By studying how snowflakes respond to varying atmospheric conditions, we might gain a deeper understanding of how precipitation patterns are likely to shift in a warming world.
So it's like those snowflakes are these, like, tiny messengers carrying information about our planet's past, present, and maybe even its future.
Precisely. By unraveling the secrets encoded within snowflakes, we might gain the knowledge that we need to adapt to and mitigate the challenges of a changing climate.
That's amazing. This has been a truly awe-inspiring deep dive. I feel like I've gained a whole new level of appreciation for the intricate world of snowflakes.
Well, it's been my pleasure to share this journey with you. And remember, listeners, the next time you see snowflakes falling, take a moment to appreciate their beauty and the profound scientific stories they hold.
Beautifully said. And before we say goodbye, let's leave our listeners with one final thought-provoking question to ponder. You know, we learned that scientists can create nearly identical snowflakes in a lab. But could we potentially engineer snowflakes with specific properties or shapes in the future? What implications might that hold for fields like material science or even like climate engineering?
That's a fantastic question. It really it sparks the imagination and invites us to consider the boundless possibilities that lie at the intersection of science and nature.
It's definitely something to contemplate as we continue to explore the mysteries of these fascinating icy wonders. Thanks for joining us on the Deep Dive.